Hello there. This is Al, and I was just having a look here to find something because I studied physics in my past, and I remember taking group theory courses, and I was just trying to find some applications and so on. And what I found instead, well, lots of examples of that where group theory is used pretty much everywhere. But some comment at the bottom of this paper. With fewer students of advanced students, and worse prepared students at that, this material is becoming less and less known. A definite reversal of trends since the 1960s. No one pays people to do group theory or quantum mechanics, well, that's true. In modern mathematics departments, it seems as unfashionable as complex variables. Another field that's too difficult these days. What he's referring to is something called complex analysis, which is a wholly different beast than the real number variety, and it is very, very, very difficult. And so for some reason, it's so difficult that nobody's learning it anymore. The really hard work to master quantum mechanics also seems to be beyond today's students and tomorrow's faculty. It can only be the hobby of a few, and I hope there are enough minds fascinated by it to preserve it as a living science. No one who is unprepared is likely to make anything of the literature in the field, and that's true. Much of the recent literature is not worth reading, and there's much to be known, but very little progress has been made recently. Collapse of foundations will make further progress very difficult. There's a search now for the Higgs boson. This is in 2000. Contemplate how few people have the faintest idea of what that means. I have contemplated that. The answer is almost no one. This bit at the end involves symmetry breaking. Is in reference to the fact that much of the work, almost all of the work, where group theory is applied, has to do with symmetries. Symmetries in physical law are, the essence essentially of physics itself, at the level of theory. Symmetries in physics are the properties that give rise to physical laws. Laws of nature are born of these symmetries which are described and understood through knowledge of groups. Now you probably think that this stuff, four measly axioms, and something that looks a little bit like a number one, there wouldn't be much to it. Well, it turns out that group theory itself, and I know by direct experience, is a subject which becomes quite difficult, and it becomes very difficult very fast. And in fact, group theory was the first course in mathematics that I felt that I wasn't sure if I was going to be able to pass. I'd never felt that way before about anything in mathematics. I did pass, by the way, which puts me apparently in a category unattainable in this year 2014. The first thing I clicked here, the third article, Wikipedia, looking for something simpler to show you, starts out with this. This article needs attention from expert in physics. Okay, now this is the world, right? Asking that this resource is a resource available to the entire world, and apparently the entire world does not consist of a single expert in physics who can look at this article and judge its correctness. Well, at least nobody willing to take part in this. Let's see. There must be some issue. There's an issue somewhere, and they would like somebody to explain what the issue is. Okay. Well, it's been a long time for me too, and I've forgotten most of it. But at the simplest level, before it becomes massively impossible to follow, it's still pretty simple. And it is, in fact, a very simple idea. 4 axioms, and we have some objects and an operator that's associative and has, in this case, this one's being defined with right-handed identities and inverses, and what you'll see later on is that this choice is actually arbitrary. And in fact, most group theory books or linear algebra, which use the same sort of similar axioms, don't identify a right or left inverse, because you can prove later that the inverse element, if there were a right inverse element, then it would be equal to the left, sorry, not inverse, identity element. So if there's an identity element, it's both a right identity and a left identity, and the same follows for inverse, turns out. Anyway, back to simple things. Oh yes, the thing I forgot. I forgot to mention last time about the 4 axioms, that they are, you can probably guess, they are all independent of each other. You can't derive one from the other. There is, at the most basic level, it cannot be reduced any further. So what I wanted to do here was just give you a couple examples of some groups that are easy to understand. Okay, and I'll show you how to prove something is a group or not. Now here's one example. A set of all positive rational numbers with ordinary multiplication taken as the operator. And you can write that this way. This notation is quite common. Some form of bracket. The identifier for if it's in a set of numbers, in this case positive rationals, and the usual symbol for its product, or the product or binary operation being used. So this just tells us that I'm saying gamma is positive rationals with times. So it has to satisfy the 4 axioms. First, is it closed? Let A and B be elements of the set of the group, or potential group, and that implies that I can write A and B this way, where M1 and N1 and M2 and N2 are both members of the positive integers. You might argue with that and say that, well, I could also write minus M1 over minus N1, correct? And that's true, but even if you did that, the answer would still come out positive, and so we wouldn't have escaped the set. Our result is positive always, and there's no way to generate through multiplication a negative value if any one of these were represented as negative integers divided by each other. Okay, that's easy to show. You can suppose that it's possible and then produce a contradiction quite easily. Okay, so then the product A times B is given by this regular multiplication, and that gives M1 M2 over N1 N2, which I've defined as K over L. L being this product and K being this product. Both of these are, that should say naturals. And then plus, meant to indicate integers. And the ratio of integers gives us the previous statement was weaker than this one. Ratio of integers gives us a rational number by definition, and so therefore the product is in the positive rationals, and it satisfies axiom 1. Next, axiom 2. Are the elements associative? Well, you would have to, you can almost just say that immediately without thought, because it's known that multiplication is associative, but I've multiplied it out using the integer representations to show how one might go about showing associativity, given that you know that integer multiplication is associative. So here I've generated A times B times C, and that's good. A, and then B times C is this ratio, and then multiplying by A gives you this ratio, the top being a positive integer and the bottom being a positive integer, and so this, we already know that it's closed. Doing it the other way around results in the same ratio, and so therefore the associative law is satisfied And there's something underneath there. Okay. So this associative law is true for all A, B, and C. Push that over. Let's see. That somehow got pushed to the wrong side. So this is true for all A triplets A, B, C in our set. So associativity is satisfied. Axiom 3, identity. Right identity, really. We're dealing with our definition that we've been given is one that involves a right identity. You could equally use a left identity. And you can also use neither right nor left, but that part hasn't been proved yet. Okay, so now all that matters is that we identify a rational number that can act as a right-hand identity for every rational number. Such a number is 1. Any rational number times 1 is equal to itself. So that satisfies the principle. So I exists. And now we would like to find an inverse, a right inverse for any element of the set. Here's my A again. And then I'm just doing the obvious. Let's choose, how about n over n, which is possible only because 0 has been omitted from our set, so there's no possibility that m or n can be 0. So therefore x exists and is a member of the set, and its product on the right of A gives us 1, which is our identity element here. So that's it. We have inverse, all 4 axioms satisfied, so that forms a group. Let's see now, another one that I came up with. These ones are very easy ones. Set of integers with plus. Okay, all integers, positive and negative, using the plus operator is a group. Again, another one that has infinitely many elements. The right identity is the number 0. Any integer, I can make it more explicit. Use n for integers. Star I, which is by this definition, n plus 0 equals n for all n. We've defined I to be 0, and we have star defined as plus, so n star I is the same as saying n plus 0, and that gives you n. So we've identified the right identity, and the right inverse for any element is simply the negative of that value, as that. I can also make this more explicit. What that's saying is that n star minus n is by definition, fix that. n plus minus n, which equals 0, which is equal to pi. Right? So we found for each n, each element of this set, a number, an element, another element, such that when we put it on the right and use the star, which is plus, with it, that results in the value 0, which is the definition of our inverse. So we have a right inverse, we have the identity, it's closed, and what else do we? Oh, it's associative too. I didn't show that. Now here's another one that I haven't shown associativity for either, but it is associative because multiplication. Sorry, not because of that. I can't use that as an argument. That is an argument, but I'd have to show you how I generated this group in order to apply it. Here's the group. First, I'm defining this group as having 3 elements labeled 1, 2, 3. I could call them A, B, C, 2, doesn't matter. And I'm defining it in such a way that it's commutative, that this operator is commutative, although I've written them all out explicitly. So here are all the possible products and their values. 1 times 1 gives 1. 1 times 2 equals 2 times 1 equals 2. 1 times 3 equals 3 times 1 equals 3. So we have a right identity, right? Just by looking at this column, right? The number 1 is an identity for element for this group, assuming it's a group. 2 times 1 gives 2. 2 times 2 gives 3. And 3 times 2 gives 1. Okay? So therefore, 2 and 3 are inverses of each other, it turns out. The commutative rule. And that's why we find that same repeated here. And here's the last set. Turns out that 3 times 3 gives you 2. So a group of 3 elements, it's self-consistent, it happens to be associative, it's closed, there's a right identity, each element has an inverse, 1 is itself, 2 has 3 as an inverse, and 3 has 2 as an inverse. Everything has an inverse. And the only interesting product is this one. It doesn't involve any inverses or identities at all. And it's the only such product with that property in this group. And it's a group. It actually has a special name. Now, some examples of things that are not groups. The set of integers under normal multiplication times is not a group. This one fails axiom 4. For instance, 2 has no inverse in this set. The identity element would be 1, because 1 times any number, integer or otherwise, gives you the same number. But there's no integer number we can multiply by 2 to get 1, so 2 doesn't have an inverse, and so therefore it's not a group. The set of positive integers under addition is not a group, and that's not a group because axiom 3 fails. There's no identity. The identity element, worth or 1, would be 0, but we've excluded that here. The set of real numbers under multiplication is not a group. because axiom 4 fails. Axiom 4 inverse the identity element would be 1 for multiplication. Okay, 1 times anything gives anything back. But not every element in this group has a inverse. In particular, 0, which is included, has no inverse. There's no real number we can multiply by 0 in order to get 1. So that's not a group. And here's another weirdo one I made up to try and find something to fail a different axiom. Set of integers under exponentiation, that is, I've defined the star operator this way. A star b is a to the b, is not a group. Now this is set of integers, positive or negative, right? And we can say immediately this is not a group by selecting a equals 3, say, and b equals minus 2. Then a times b is 3 to the minus 2, which is not an integer, and it's not in the set, and so this one is not closed. Okay? And lastly, I'm going to leave this for you to think about. The 3 main first theorems that we would like to have proved before proceeding. I'm going to leave for you once the next video is up, then anyone can just click to the next video and see the answer. But I would advise at least spending some time to try and see if you can do it yourself. It's not that hard. And as I mentioned before, in a lot of texts, axioms 3 and 4 are written with no reference to right or left. Okay? And the following theorems demonstrate that the equivalence of left and right identity and inverse, as well as uniqueness. And that's a bit more tricky to show. And I'm just stating the 3 main theorems that establish that. Okay? Theorem 1. So get out your pencil and paper, write it down. A group. Now these are all provable by applying the 4 axioms. Okay, just mechanically applying the axioms. You don't have to appeal to anything. The axioms will give you these results. A group contains only one identity, I. It is both a right identity and a left identity. Okay, so that means a left identity is something that has this property for every element in the group. Just the opposite. 2, if A and X are elements of the group, gamma I've called it, and supposing A times X equals I is unique, but we haven't proven that yet. Is equal to some I, some identity, then it follows as well that X times A with A on B right now and X on the left is also equal to I. Okay? Now further, there is no element in the group other than this X that satisfies either of these equalities. So X is unique. Okay? Now X is called the inverse of A. And we can say the inverse because it's unique. And it's typically written like that. Well, in accordance with the usual notation for inverses. There's no meaning assigned to that -1 other than that it's an inverse. Okay, there's no division going on or anything like that. It's just a handy notation that you're familiar with and that you would expect to cancel, with an A and give you something like 1. I here is analogous to 1. If this was times, although it could be plus, in which case I is analogous to 0. In those cases, we write, instead of -1 here, we put a minus in the front. If A and B are two elements of the group, then one and only one element of the group satisfies this equation. A times Y equals B. Okay? Now, it didn't state it. It didn't state it. Oh no, it does say that. I'm sorry. The identity I is unique is stated right away here. Only one identity. There is no other element of a group that acts as an identity. If there is one, then it's the only one. Okay. So those are the three theorems that establish the uniqueness of inverses and identity and of solutions to equations of the form this. B is some element in the group, A is some element in the group, A times A star something equals B has a unique solution. Okay? That can be proven. All these can be proven from those 4 simple axioms. Now, at this point, all of this should be easy and understandable, and I won't let it progress too far so that it becomes impossible to follow anymore. Okay? I'll only go up to a certain point and hopefully come up with enough interesting examples to get somebody out there interested in learning group theory. Because once that's gone from the planet, that spells the end really for progress in the sciences, especially in the physical sciences. This knowledge can't disappear. Even if it's written down in books, doesn't mean it's there. Just because something is copied on the internet doesn't mean it's there. It just means that there's some writing, and if nobody understands the writing, then it's completely useless, right? It's hard work to understand this stuff at the higher level, but it's well worth it to learn this stuff, and it's very interesting, and the theorems and proofs are extremely clever and inventive, and it's an enjoyable experience, but a hard work experience, but it has its rewards. Okay, till next time.